Hi guys, I'm Monica. Welcome back to my channel Aeroker. So in this video, we will be discussing about doublet flow, which is one of the elementary flow again. In our previous video, we had seen a case where we superimposed uniform flow on the source flow, and then we placed source flow and sink flow beside each other and superimposed uniform flow on that. So what is it about the doublet flow? What kind of elementary flow does it form is what we are going to look into this video. So without any further delay, let's get started. So here you have to consider a source of strength lambda and a sink of strength minus lambda. So as discussed in our previous videos, this is the capital lambda. Now this sink, which is of strength minus lambda, is equal, but it is opposite. That is why it is minus. And they are separated by a distance L. So over here, let us say this is my lambda, which is the source, and this would be minus lambda, and they are separated by a distance L. So this whole region, what you're seeing is the flow field, and in that flow field we have considered this source and sink. Now at any point in the flow field, let us say here somewhere here, I'm considering this point as P. So at any point P in the flow field, if I want to write the stream function, it can be written as something of this sort, lambda by 2 pi theta 1 minus theta 2, which can also be written as lambda by 2 pi into delta theta. Let us say this is our equation 1. Now this delta theta is nothing but your theta 1 minus theta 2, which would be this angle. If you have to note it in the figure, this would be your delta theta. Where would be theta 1 and theta 2? So this is our theta 1, and this would be your theta 2. So now this equation 1 is nothing but the stream function of source sink pair, which is separated by a distance L. We will assume one condition, or let us say that this distance L is tending to 0 or approaching to 0, while the absolute magnitudes of the strengths of source and sink increase in such a fashion that the product L lambda, that is L lambda, remains constant. So this is what is the condition we are considering. Now when the limit L tends to 0 and L lambda remains constant, the flow pattern you get is what we call it as doublet. Now, the strength of this doublet is denoted by this letter, which is known as kappa, and this K or kappa, not K, kappa is equal to L lambda, that is L into the strength of source. The stream function for a doublet, if I want to write it for a doublet flow, using equation 1, I can write it as this sort: psi is equal to limit L tends to 0, and kappa is equal to L lambda is equal to constant, which is minus lambda by 2 pi into d theta. Let us say this is our equation 2. When in the limit delta theta tends to d theta, which tends to 0, this happens in the limit. One point to be noted here is that source strength lambda approaches an infinite value in the limit. When we are applying this limit, the source strength approaches an infinite value. So this second figure over here, what you're seeing is nothing but this limit where the L is decreasing, and this is our point P. This would be your d theta, and this is your theta. If I draw a line from sink perpendicular to R, this is my R. So this R and B are the lines that are denoting the distance from source to P and sink to P, R and B. So what will I do is I will draw a perpendicular line from sink, that is from here to R. So this is the perpendicular from sink to R, and I will denote this length by A. Infinitesimal d theta, if we look at this geometry, let us say this is our figure B and this would be our figure A. For infinitesimal d theta from this, and also referring the geometry, I can write A is equal to L sine theta and B is equal to R minus L cos theta. So d theta would be A by B, 3. Now let us substitute equation 3 in 2. So upon substitution and mathematical manipulations, I would get the stream function as kappa by 2 pi sine theta by this is our equation 4. So what is this equation for? It is the stream function for doublet. Similarly, I can write velocity potential for doublet as kappa by 2 pi into cos theta by R. This would be our equation 5. Now if I want to write the equation of streamline for the doublet flow, what would be the simple procedure? To set the stream function is equal to constant, that is kappa by 2 pi into sine theta by R is equal to constant, which would be C. Or I can also write this equation as R is equal to minus of kappa by 2 pi C into sine theta. This is another form we can write. Let us say this is our equation 6. Now this equation 6 is our equation for streamline for a doublet flow. Now from analytical geometry in polar coordinates, I can write R is equal to d sine theta in terms of polar coordinate. This would be my equation 7. So this is a circle, this equation, it is a circle with a diameter d on its vertical axis and with the center located at d by 2, that is directly above the origin. Now if I compare these two equations, that is equation 6 and equation 7, what can I say? That streamlines for a doublet family, doublet are a family of circles which are of diameter kappa by 2 pi c, if I am comparing these two equations, correct? So if we have a look at this figure which shows the doublet flow, you can see they are the concentric circles, correct? So now in this, different circles correspond to different values of the parameter C. Every circle will have different value of C. So now if we look at figure 1, what if I place the source to the left of the sink? The direction of the flow is out of the origin to the left, and back into the origin from the right. So from the right, it is coming back into the origin. Vice versa, if I place sink to the left of the source, that is, I take the sink and place it on this side over here, what will happen? The first thing that is going to happen is the signs of equation 4 and 5 would be in opposite direction. The signs would get reversed, and the flow which you are seeing over here, that would also get reversed in direction. From these considerations, we can say that a doublet is something which is associated with a sense of direction, the direction in which the flow moves around the circular streamlines. So by convention, we designate the direction of doublet by an arrow, that is from the sink to the source. Now in figure 2, if the arrows point to the left, if the arrows are pointing towards the left, which is consistent from equation 4 and 5. But if the arrows are pointing towards right, then if the arrows are pointing towards the right, what would happen? The sense of rotation would be reversed. Equation 4 will have a positive sign and equation 5 will have a negative sign. So these are the possibilities of the flow directions, or depending on the direction of the flow, we can know the sign of the equation. So now, as we saw here in figure 1, as L tends to 0, what happens to source and sink? They fall upon each other, correct? But they do not, however, they do not extinguish each other, because the absolute magnitude of their strengths become infinitely large in the limit, and we have a singularity strength in this case. So this is an intermediate form, and this can have a finite value. So before we end our discussion on doublet, what is a doublet? A doublet is a singularity that induces about it the double-lobed circular flow pattern, as you can see in this figure. So this was a small discussion on doublet that we had. Thank you for listening. Stay tuned.